When you look at a brief 100-line algorithm, it gives the illusion of simplicity. It looks contained. It seems like it should be easy to run a few tests and guarantee it works. But add a few nested loops and branching decisions, and the execution paths multiply into a massive, chaotic web. Take a standard 100-line program. If you put 4 simple if-then-else constructs inside a loop that runs 20 times, that single structure yields roughly 100 trillion possible execution paths. If you could execute one test every single millisecond, it would still take over 3,000 years to run through every possible path in that tiny block of code. This is why software engineers use white box or glass box testing. This approach uses the known internal control structure of the software to strategically select a subset of tests. True software reliability cannot rely on infinite time. It requires a surgical mathematical model to isolate the exact mandatory paths that verify the code's operation. The first step in basis path testing is translating lines of procedural code into a purely topological map called a flow graph. Looking at this side-by-side comparison, standard sequential code statements are abstracted into circles. We call these nodes. The flow of control, the direction the computer reads the code, is represented by the connecting arrows, called edges. When the code hits conditional statements, like an if or while command, the node splits into multiple edges. These are called predicate nodes. Any empty space fully enclosed by intersecting nodes and edges is defined as a region. The entire external area outside the graph also counts as one distinct region. This visual translation strips away the distracting syntax of programming languages, exposing the raw mathematical skeleton of the algorithm for rigorous analysis. With the flow graph built, we calculate a quantitative metric of the program's logical complexity. This is cyclomatic complexity, denoted as V of G. Calculating V of G provides the exact upper bound for the number of independent paths needed to achieve 100% statement coverage. Here is a complete flow graph. The first way to calculate V of G is by counting the total number of visual regions on the graph, which includes the outside area. Here we have 3 enclosed regions, plus the outside, giving us 4. The second method uses the structure itself, counting the total edges, subtracting the total nodes, and adding 2. 11 edges minus 9 nodes plus 2 also equals 4. The third method is even simpler. We isolate the branching predicate nodes and add 1. 3 predicate nodes plus 1 equals 4. All 3 mathematical formulas yield the exact same integer, proving the topological consistency of the model. This single calculated integer provides the absolute target number of test cases required to guarantee that no line of code goes untested. An independent path is any route through the program that introduces at least one new processing statement or a new conditional edge. The tester traces these discrete routes through the graph one by one. You stop mapping when the total number of paths equals the V of G integer we just calculated. Once these routes are mapped, they form the basis set. Testers write specific inputs, forcing the software to travel down those exact paths during execution. To scale this process, the visual map is converted into a square matrix format that computers can process. Rows and columns represent nodes, and the intersections represent the edges between them. Automated software uses this matrix to instantly calculate path probabilities, memory usage, and execution times without human intervention. Cyclomatic complexity and graph matrices elevate test case generation from human guesswork into a scalable, automated engineering discipline. Basis path testing guarantees every statement is read. However, bugs can still hide within the boundaries and specific data states of those paths. Software often fails at its structural seams. To catch these, testers use condition testing. This targets complex Boolean logic, ensuring both true and false outcomes are explicitly evaluated for every condition. Data flow testing selects test paths based on where variables are defined versus where they are ultimately used. Tracing definition use chains prevents data corruption. Finally, algorithms rely heavily on loops. There are 4 unique classes of loops to test: simple, nested, concatenated, and unstructured. A loop designed for a maximum of n passes requires strict boundary testing. You must explicitly force 0 passes, 1 pass, 2 passes, a typical m number of passes, n-1 passes, and exactly n passes. Layering condition, data flow, and loop tests over the primary basis set ensures the most complex data states and branching paths are systematically exercised. A developer abstracts code into a flow graph and calculates cyclomatic complexity. This isolates the independent paths into a basis set. Testers add structural stress tests for loops and conditions, creating a complete white box test specification. This highly structured framework completely replaces the impossible 3,000-year burden of exhaustive testing with a finite, manageable checklist. But white box testing has one critical blind spot. It can only verify the code that actually exists inside the file. No amount of internal graphing can detect missing requirements, forgotten features, or high-level behavioral failures. If the wrong function was coned, the math will perfectly verify that wrong function. White box testing verifies the internal structural integrity of the machine, but developers must ultimately rely on black box testing to ensure the machine actually solves the user's problem in the real world.